Problem set 3.1, problem number 11. Some parts of this are very rudimentary, other parts require deeper thought. A 10-kilogram block is gently released on top of an uncompressed vertical spring with a spring constant of 500 newtons per meter that is attached at the other end to the ground. So we'll start off with a diagram, get our bearings. So here's the ground, we've got a spring which is initially uncompressed. We're going to place a mass atop that gently, which tells me that the velocity is 0. I'm placing this block on top of the spring and releasing with no velocity, no kinetic energy. So, of course, that spring is then going to compress as a result of this weight that is being placed atop it. So I will draw a compressed spring, and it's gonna drop like that. Now, take a moment to think about what an object dropped or released on top of a spring will do. If there's no loss of energy, if there's no friction, this object that is released on top its weight will cause the spring to compress, but then it's going to gain speed as it does so. And then eventually, once the spring compresses enough, it's going to slow that block down and bring it to rest at the bottom. But just like a pendulum, it will have carried itself past its equilibrium point. It will coast past the equilibrium point to where the spring is compressed quite a lot, and that spring force will then push it back up, and then it will rise, and then eventually the mass will essentially become, and the spring will become uncompressed. It will reach its initial height again, and but basically that will continue, just like a pendulum. It swings past its middle equilibrium point to the other side and back and forth. So this is what we call a spring pendulum or vertical pendulum. So what we want to know is, what is the max compression of the spring? Essentially, how far is this spring going to compress before it stops and turns around and goes back up? So what happens there is, at that point, since it's coming to rest, at that point, there is no kinetic energy there either. So at the top, the velocity is 0, and at the bottom, the velocity is 0. So what we do have is gravitational potential energy turning into spring potential energy. So at the top, draw it like this. We can say, there's some height here, call this height 1, and this height 2. And since the block started on the spring and compressed the spring, we can also recognize that the change in height is exactly equal to the amount that the spring is compressed. So that's convenient. The change in height is equal to x, so we can employ that very soon. So now the question is, what is the max compression of the spring? So we acknowledge that at point 1, there is some gravitational potential energy, and that's it. It's not moving and there's no compression. So at point 2 there, if we call height 2 to be the lowest point it can reach, 0, we can say that there is no potential energy at that point either, because it can't get any lower. There's a spring in the way. So at that point, gravitational potential energy at point 2 will be 0, and so all that there is would be spring energy at point 2. So we've got mgh equals 1/2 kx squared, where just a moment ago we mentioned that the height that it falls through is the same as the distance that the spring is compressed. So this height that it starts from down to 0 is x. So I'm going to replace that. I'm going to substitute that in. It gets rid of a variable. mgx equals 1/2 kx squared. This x will cancel out the squared of that, and at this point we can solve for x. So I got mg equals 1/2 kx. So if I rearrange this, I get 2 mg over k equals x. And plugging those values in, I get 2 times m, which is 10, times g, which is 10, over k, which is 500, equals x. So that's 200 over 500. That's 0.4 meters is the amount that it's going to compress from release to the point where it has sort of fully compressed the spring. Can't go any lower. So I'm going to need a little bit more room. So I'm going to shrink that down, move that over here. Grab you, move you over here. And now let's consider part B. It asks, find the compression of the spring corresponding to the maximum speed of the block. All right, I'm actually going to bring this over because at the top, at 0.1, and the bottom, 0.2, somewhere in between there, it will be going the fastest. At the top it was at rest, at the bottom it was rest, at the top it was at rest, and the only force was mass times gravity. At the bottom, because it is being decelerated and forced to stop, and then it will go back up, at that point, the spring force is larger than the weight, because it's stopping it and reversing its direction. So there's an acceleration upward due to the compression of the spring. So somewhere in between there is a point, and here's the tricky part of it. Now, in part one, it's decelerating downward, or it's accelerating downward, because there is a net force downward. At point two, it's accelerating upward because there's a net force upward. So as long as the net force is down, it will speed up in its descent. Once it reaches a certain point, the forces will be balanced. At that point, it will no longer be speeding up, and if it goes further, the spring force gets to be larger, and at that point, the net force will be upward. So really what we're looking for is the point where the forces are balanced. There's no longer any acceleration. It's not accelerating downward. It's not picking up speed. It's not slowing down on its descent. So we want to know what's going on at that point where mass gravity equals the spring force. When the forces are balanced, that is the point where it's reached its maximum velocity. So even though this is an energy question, recognizing that forces play a role is pertinent to this. So the point where the spring force equals mg, so that's the kx, how much force is there? We'll use absolute value. It kind of doesn't matter. It's just a spring compression. We need to find a magnitude. How far is it compressed? Equals mg. So we know k, we know m, we know g. So the compression for this moment is going to be mg over k. So m was 10, g is 10, k is 500. So that's 100 over 500, 1 over 5. So that's corresponds with a position of 0.2 meters of compression. It has fallen 0.2 meters. So for part C, we want to know what is that maximum speed. Well, we want to know what the speed is that corresponds with that location. So for this part, I'm no longer going to consider the bottom of or full compression to be the 0 point of its height. Instead, let's concern ourselves with how much energy it has changed from its maximum height down to that point. So let's, this some point in the middle, right here-ish, it has fallen by 0.2 meters. And that will also be the amount that it compresses. So the potential energy at 0.1 is going to equal the spring energy at 0.2 plus, of course, there's some kinetic energy there at 0.2. So since it will have fallen 2 meters by then, we can say that it started at a height of 2 meters. So mgh, where height, 0.2 meters, 2 meters. equals 1/2 kx squared plus 1/2 mv squared. So mg, so that's 10 times 10 times the height of 0.2 meters equals 1/2 k, which is 500, times 0.2 squared plus 1/2 the mass, which was 10, times v squared. So this is what we're left with to solve. 10 times 10 is 100, 0.2 of that is 20, 1/2 of 500 is 250, 0.2 squared is 0.04, 250 times 0.04 is 10, plus half of 10, so that's 5v squared. So let's move things around. 20 minus 10 is 10. 10 equals 5v squared. V squared equals 2. V equals radical 2. This is approximately 1.4 meters per second. Thanks.